Now that we know how to do confidence intervals and hypothesis tests for a single proportion using a single sample, it's time to turn our attention to two-sample inference, or inference for two populations. This comes up in a variety of contexts. Probably the number one way this comes up is when you have an experiment and there's two treatment groups and you're testing to see if there's a significant difference between the way the treatment groups responded to their treatments. But you could also ask questions like, is the average SAT score for one group of people or one population significantly different than the average SAT score for a different population, and other such questions. So just like we did before hypothesis tests and confidence intervals for single proportions, we need to look at sampling distribution, and we need to look at the sampling distribution of x bar 1 minus x bar 2, the difference between two sample means. So recalling what we know about the sampling distribution of x bar, the mean of the x bars is the population mean, and the standard deviation of the x bars is the standard deviation of the population divided by radical n, and under certain circumstances the distribution of x bars is approximately normal. And we have a set of conditions that we're supposed to check to make sure that each of those three things is true. By the way, I just took both sides of this and squared it because a little bit later on we're going to need to talk about variance instead of standard deviation. So this is not really one of the conditions. And there's something important that way back when we referred to as the Pythagorean Theorem of statistics. It's about the variance of a sum of two random variables. The variance of the sum is the sum of the variances. And you might recall when we went over this that it's also true for difference, meaning that the variance of a difference of two random variables is still the sum of the variances. Also for independent random variables, the mean of the sum is the sum of the means, and the mean of the difference is the difference in the means. So we're going to use that to help us figure out something about the distribution of x bar 1 minus x bar 2. So the independent random samples we're going to have here, or I'm sorry, the independent random variables we're going to have here are the x bar 1 and x bar 2, the sample means from our two different independent samples. And they're possibly based on two different sample sizes, n1 and n2. So the mean of x bar 1 minus x bar 2 is, so the mean of the difference is the difference in the means, and the variance of the difference is the sum of the variances, which would look like this, or if we take the square root of both sides, it would look like this, standard deviation. So similar to the 3 bullet points we had for the distribution of x bar, the mean of the x bars, the standard deviation of the x bars, and the x bars being approximately normal, we have something similar for the difference between two independent x bars. The mean of the difference between the x bars is the difference between the population means. The standard deviation of the difference between the x bars is this radical expression, and the shape of the difference between the x bars is approximately normal, and we have similar conditions that we had before. The main thing is not only do we need random samples, but we need them to be independent random samples. Still should be taking less than 1/10 of each population, and still both of our sample sizes should be at least 30. So recall that a couple chapters ago we tweaked this z-score formula into a formula for turning x bar into a z-score by subtracting the mean of the x bars and dividing by the standard deviation of the x bars. And then also remember, one key point happened when this sigma was replaced with s, then this quantity, instead of giving us a z, gives us a t. So we're going to see something similar with the two-sample case. Remember that this formula involving t was basically our formula for a one-sample t-test, and a slight modification of that formula or a rearrangement of that formula became the formula for confidence interval, a t-interval. And also remember, dealing with t, we had something referred to as degrees of freedom, which back then was just n minus 1. Okay, so in the two-sample case, we take the difference of the x bars, we subtract the average difference of the x bars, and we divide by the standard deviation of the difference of the x bars. And the mean of the difference of the x bars is right here, and the standard deviation of the difference of the x bars is here. So we plug those two in, and we get this expression here. So the difference between the x bars minus the difference between the population means over this radical, which is the standard deviation. So that's how we turn a difference of x bars into a z-score. But if we don't know the sigmas, which would be the population standard deviation for each of the two populations, then we would have to replace those with s's, which is the sample standard deviation for each sample. And when we do that, this expression, instead of giving us z, gives us t. So that will be our formula for a two-sample t-test, and it'll also form the basis for a formula for a two-sample t-interval, which will look like this. That same radical that's in the denominator here appears in that part of the formula there. One little complication with these two-sample procedures is that degrees of freedom is a little bit tough to come up with by hand. It's not something simple like n minus 1 like it was before. This ugly formula is used to calculate degrees of freedom. But I don't think you're going to ever be asked to use that formula by hand. The calculator has that formula built in. But I just want you to be aware of this ugly formula because the calculator will spit out degrees of freedom as a decimal number, and I want you to be aware that when you see degrees of freedom as a decimal number, it's because of this ugly formula here. So let's work an example to illustrate how these formulas get used. We have a random sample of 35 students selected from Cal Poly Pomona, and they were found to have an average SAT score of 1190 with a standard deviation of 91. So that's the mean and the standard deviation of our sample. We have a separate independent random sample of 32 students selected from Cal Poly San Luis Obispo, and they have an average SAT score of 1310 with a standard deviation of 82. Is this convincing evidence that there's a difference between the average SAT score at Cal Poly Pomona and Cal Poly San Luis Obispo? So just as in a one-sample t-test, we start off our two-sample t-test by writing a pair of hypotheses. The null hypothesis is that the average score at Cal Poly Pomona is equal to the average score at Cal Poly San Luis Obispo. The alternative hypothesis is that those two population means are not equal. Notice that if the population means are equal, then that means their difference is 0. And if the population means are not equal, then that means their difference is not 0. And over here I've defined what those two mu's stand for. There's the name of our test, two-sample t-test, and the formula. And then some of the notation plugged in from our problem. Instead of subscripts of 1 and 2, I'm using subscripts of P and SLO. And also notice that this little term right here, the difference in the means, the difference in the population means, that difference is 0 according to the null hypothesis. So that's why when we go from here to here, you'll see that this term here drops out because that difference should be 0 according to the null hypothesis. So we check our assumptions. We have 2 random samples. They're stated to be independent random samples. The sample sizes are both less than 1/10 of the population, assuming that these schools have thousands of students. Both sample sizes are greater than 30, so the distribution of x bar 1 minus x bar 2 is approximately normal. All those conditions have been met due to the number crunching. So the formula we had earlier, we plug in the 2 sample means from our problem, the 2 sample standard deviations and the sample sizes, and we get a t of -5. This is the only time I'm going to do this calculation because usually I will let the calculator give me this calculation. This is the calculation for the degrees of freedom, and the probability of a t being less than -5 is about this. And since we had a 2-tailed test, we multiply by 2, and we get this, which is still incredibly small. In fact, on the calculator, it shows up in scientific notation. Because the p-value is so small, we reject H0. There's strong evidence that the average SAT score for all students at Cal Poly Pomona is different from the average SAT score for all students at Cal Poly San Luis Obispo. We have evidence that this population mean is different from this other population mean. Let's take a look real quick at how this would look on the calculator. So we go to our normal location on the calculator, stat tests. And we're going to go down to 2 sample t-test, highlight the word stats, and let's enter the x bar from our Cal Poly data and the standard deviation for our Cal Poly sample and the sample size for Cal Poly. Let me just double check those numbers. And then we're going to enter our x bar for the Cal Poly San Luis Obispo sample and that standard deviation and that sample size. Our alternative hypothesis says not equal to. There's this term pooled that we haven't talked about, and by default that is marked as no, and we're just going to leave that no. And then it's time to calculate. And there's our t of -5.6. And degrees of freedom, 64.9. Same as right here. P-value is in scientific notation, 3.4 times 10 to the -7th, which is this number right here. So the number crunching part of the operation is verified by the calculator. Okay, so the second part of this would be, or the second part of 2 sample inference for means would be to do a confidence interval. So let's say for the same data, let's say we were asked to construct and interpret a 95% confidence interval for the difference between the average SAT score of all Cal Poly Pomona students and the average SAT score of all Cal Poly San Luis Obispo students. So the formula that we had up here, right there, formula for a 2 sample t interval. So we plug in our 2 x bars. We plug in our t star. Now we already know the degrees of freedom is 65, roughly 64.988. If we do inverse t, we do inverse t with a tail area of 2.5% for a 95% confidence interval and degrees of freedom 65. We get a t star of 1.997. So that's why this one here. And then this is the same radical that we had before. So this is -120 plus or minus our margin of error, which gives us a confidence interval from -162 to -78 roughly. And then we can verify that also on the calculator. Stat tests to sample t interval. And again, enter the mean, the standard deviation, and the sample size from our first sample, the mean, the standard deviation, and the sample size from our second sample. Indicate the confidence level. Pooled should say no, and calculate. And there's our negative 162.2 and negative 77.79. So then the interpretation, we are 95% confident that the difference between the average SAT score of all Cal Poly Pomona students and the average SAT score of all Cal Poly San Luis Obispo students is between negative 162 and negative 78. So hopefully you feel like that the flow of this is very similar to one sample procedures. The steps are similar. The interpretation of the confidence interval is similar. The decision on whether or not to reject the null hypothesis is the same. We just have slightly different formulas because we're dealing with two samples, but we don't really need to get bogged down in those more difficult formulas because all these calculations will be done for us by the calculator. Okay, so now let's take a look at how all of that works in the world of proportions. So we're still going to take two samples from two different populations, but now instead of looking at the population mean and the sample mean, we're going to look at the population proportion and the sample proportion. For example, if we wanted to investigate if the proportion of unregistered cars in the parking lot at Cal Poly is different than the proportion of unregistered cars in the parking lot at Chaffey College. So refresher on what we know about the sampling distribution of p hat. The mean of the p hats is the population p. The standard deviation of the p hats is this radical that we should be familiar with. And the p hats are approximately normal. The distribution of p hats are approximately normal if certain conditions are met. Okay, so if we look at the difference between two proportions, then we have independent random samples. The sample proportions, p hat 1 and p hat 2, are the two independent random variables, possibly different sample sizes. So the mean of p hat 1 minus p hat 2 is just p1 minus p2, and the variance of p hat 1 minus p hat 2 is this expression, which gives us this expression here for the standard deviation of p hat 1 minus p hat 2. So for the distribution of p hat 1 minus p hat 2, the mean of the difference in the sample proportions is the difference in the population proportions. The standard deviation of the difference in sample proportions is this radical here, and the difference in p hats follows a normal distribution or is approximately normal under certain circumstances. So remember when we did a z-test for proportions, once again we tweaked our usual z-score formula a little bit to be the p hat minus the mean of the p hats divided by the standard deviation of the p hats, and we had an expression something like that. And also remember that when we were dealing with a hypothesis test, we replaced the p's over here with p subscript 0. And also remember that a variation of this turned into our confidence interval formula, which looked like that, except now this radical, instead of having p subscript 0, has p hat, because all we have to go on is the sample when we're doing a confidence interval. We don't know about the population. So if we do all of that for two samples, then our z is going to be the difference in the p hats minus the mean of the difference in the p hats divided by the standard deviation of the difference in the p hats. And the mean of the difference in the p hats is the difference in the population p's, and the standard deviation of the difference of the p hats is this radical expression here. So this is the expression for z that we're going to base all of our stuff on two samples with proportions on. Now, when we do a hypothesis test, The null hypothesis says that the two population proportions are equal, which means that their difference is 0. And the null hypothesis doesn't say what P1 is or what P2 is. It just says that they're equal. So since the hypothesis is that those two population proportions are equal, we're going to put our two samples together, the x and the n that would normally make up p hat 1 and the x and the n that would normally make up p hat 2. We're going to put those together into what's referred to as a p hat combined, or sometimes it's called p hat star. But so this is what we're going to use in the case of hypotheses instead of the radical that you saw earlier. So same radical, except now it's this p hat combined that goes in here. And since this expression in the numerator and this expression in the numerator are the same, that gets factored out, leaving us with 1 over n1 and 1 over n2. And also notice that the top of this expression has lost the, where was it out up here? It's lost the p1 minus p2 term because p1 minus p2 is 0 according to the null hypothesis. So this is our formula for our z-score when dealing with two proportions from two different populations. And then we should also do our check of the large counts condition using that p hat combined. And there's 4 of them we got to check. n1 times p, n1 times 1 minus p, n2 times p, n2 times 1 minus p. Okay, now if you go back to the z-score formula that we had originally and then rearrange this, it gives us an expression for a confidence interval using two proportions. So instead of p hat plus or minus z times the radical, now it's p hat 1 minus p hat 2 plus or minus z times the radical. So let's show you how all that would work out in a problem. I've got a random sample of 150 cars from the parking lot at Cal Poly Pomona, and 27 of those cars had expired registration. Then I have a different random sample of 100 cars selected from the parking lot at Chaffey College, and 13 of those cars have expired registration. Is this convincing evidence that the proportion of all cars with expired registration at Cal Poly Pomona is different from the proportion of all cars with expired registration at Chaffey College? So P subscript CPP, is that equal to P subscript CC, or are they not equal to? Proportion of all cars at Cal Poly Pomona with expired registration, proportion of all cars Chaffey College with expired registration. This is a two proportion z-test, and there's our formula with the combined p hat in it. We need to check some conditions, and they said that they were both random samples. They didn't say that they are independent, but we're going to assume that they're independent. And I have students in here. Each sample size is less than 1/10 the population, assuming there's at least 1,500 cars at Cal Poly Pomona and at least 1,000 cars at Chaffey College. Our combined sample proportion is this: the total number that we saw with expired registration divided by the total number of cars that we looked at or sampled. So checking the large counts with our p hat combined of 0.16, all of those are greater than 10, so we can assume that the p hat 1 minus p hat 2 distribution is approximately normal. Then here's our two individual p hats, which go in the numerator, and then our p hat combined from earlier that goes in the denominator. And this gives us a z of 1.056. The probability of a z greater than 1.056 is this, which gets multiplied by 2 to give us 0.29. Because the p-value is so large, we fail to reject H0. There's not enough evidence to say that the proportion of all cars at Cal Poly Pomona with expired registration is different from the proportion of all cars at Chaffey College with expired registration. So the phantoms acronym that we've learned before for all the steps of the hypothesis test, that's exactly the same. We just have slightly different calculations for the z, and of course our hypotheses look a little bit different and our conditions checks look a little bit different. The number crunching part of it will be handled by the calculator. This is a 2 proportion z test. So our first sample was 27 out of 150 had expired registration. And our second sample was 13 out of 100 had expired registration. And our alternative hypothesis was not equal to, and we calculate, and we get a z of 1.056, which I think is the same z that we had over here. And there's a p-value of 0.29, which is the same p-value we got right there. So all those calculations are in agreement. And just like any hypothesis test, big p-value, fail to reject. How does that look in the world of confidence interval? So let's say we're dealing with the same data, and we want to construct a 99% confidence interval for the difference between the proportion of all cars at Cal Poly Pomona with expired registration and the proportion of all cars at JP College with expired registration. Here's our confidence interval formula. We plug in our 2 p-hats. Z star for 99% confidence is 2.576, and we plug in our p-hat 1 and n1 into here, and our p-hat 2 and n2 into here, and we get a confidence interval that looks like this, from negative 0.06 something to positive 0.16 something. Just to double check those calculations on the calculator. Stat test 2 proportion z interval, 27 out of 150, 13 out of 100, and we're doing a 99% confidence interval this time. And we got negative 0.685, that looks legit, and we got 0.1684 or 85, so that looks legit. And we are 99% confident that the difference between the proportion of all cars at Cal Poly that have expired registration and the proportion of all cars at JV College that have expired registration is between negative 7% and 17%. And that's how you do hypothesis tests and confidence intervals when you are selecting 2 samples from 2 different populations.